Hello everyone, welcome to the presentation. This is Serkan Ozal. Let me introduce myself first. I am founder and CTO of Tundra, which is a debugging, monitoring and security solution for service-centric workloads. And I have been honored to be recognized and nominated as AWS Service Trio 3 months ago. And I am also co-organizer of the Cloud and Service Turkey meetup and was part of the team that organized Serverless Istanbul in 2019 last year. And I have been actively working and researching in serverless era for 4 years. If you are interested in serverless monitoring, tracing, debugging, and distributed systems, you can have a look at my post publications, open source works on Twitter, Medium, and GitHub accounts. Okay, this is the agenda of the presentation. At first, I'm going to talk about existing debugging solutions for serverless environments with their pros and cons, and then I am going to introduce new online and offline debugging approaches, and then explain what are the advantages over traditional ways. Then I am going to give some example issues which can be detected easily by online and offline debugging approaches. And I should also mention that for the demo of debugging approach, I am going to use our product Tundra when needed. Okay, let me first start with how debugging works in classical world regardless of serverless. While we are developing, we test our application on local, automatically by unit and integration tests or manually. But if you are not just printing to the console, it is expected that it doesn't work at first try. Then, to find the problem, we debug our applications locally from our IDs. We put breakpoint to the lines where we want to pass the application on and check the values of arguments, local variables, properties, and so on. But this approach doesn't work on serverless, unfortunately. So I remember that the time when I first met with AWS Lambda at the mid of 2016, I was adding print logs to the code, redeploy the app, triggering the function, and checking the logs from CloudWatch. And then, if I want to check the other parts, I was inserting more logs, redeploying, and check the application again and again. So I was spending only a very small portion of my overall time developing. Most of my time was occupied by rebuilding and redeploying the app. So I remember that I had wished to have a proper debugging solution for AWS Lambda. But because it was not easy to have the same setup on my local, so most of the time I had to debug on real AWS Lambda environment by inserting logs and redeploying the application again and again. So it was very time-consuming process for me. There are already some well-known approaches to debug service applications, and each of them has their own advantages and disadvantages. So I will go through each of them by mentioning pros and cons, and then I am going to describe the ideal solution and the way that how it should be done. Let's start with mocking. Mocking has always been the most common approach while testing applications. Mocking technique can also be used to debug the application on local, especially if your application interacts with many external services, which is a very expected case in serverless or microservice world in general. So it may not be feasible to have all the external services on local or access from local. So in this case, the external services can be mocked on local, and then service applications can be debugged by using local IDs in a traditional way. The pros are that it is doable and has been actively used by developers since years, and there are many mature mocking libraries for all runtimes and programming languages and already adopted best practices. And it doesn't require deployment as you debug on your local. And probably you are already familiar with it from your non-serverless days, and I assume that you have a life before serverless like me. And the cons are that it simulates external communication, so you are not running the application in real environment where it normally will work on. So things might behave differently in real environment. For example, some issues such as concurrency bugs might be related with the speed of host or application. CPU power or number of cores might play an important role on the reproducibility of the bug. And in addition, it may not be easy or feasible to mock or simulate every behavior of external services. Sometimes mocking libraries may not be up to date with the external service itself, so if it has new features or functionalities. other solution is simulating all the things on local. And in this approach, external services like databases, caches, queues, and APIs are simulated on local. Then they can handle requests and send proper responses according to their spec. But of course, it is not expected from simulations to have the exactly same capabilities with the real services. The pros are that it is better than mocking, as no need to effort to mock the things, just run the external service on local and update the config to point to the local host. Although simulation is not a real service, still your application is communicating with external service even if it runs on local. So it is not perfect, but better than nothing. The cons are that simulation may not be synced with the real service. For example, a new feature might be released by real service, and if you are using that feature, simulation will not be able to provide the functionality you are looking for. And it may not be easy to install external service into local, and it might require installing some other third-party tools, services, or libraries, and even it might be operating system specific, and you may need to run it in a virtualized environment on your local, and it may not be easy to maintain it, as it might be required to upgrade to the latest version, and the upgrade should be done by every developer in the team. So if the setup is not very straightforward, the maintenance might be a headache. And again, you are still running on your local and not talking with the real service. So the same disadvantages about usage of non-real service also apply here. The other approach is running serverless application on local in a simulated environment and letting the application communicate with the real services on remote. For example, AWS SAM provides a simulated AWS Lambda environment. For example, it mimics runtime specific environment variables and allows you to run and invoke your Lambda function on local. And like others, this approach also has its own pros and cons. The pros are that applications communicate with real services on remote, so no local setup is required, and you can use latest features. And you can use your favorite local ID to debug the application, to debug the function as it runs on local, and you can attach its process. And the toolsets for developing and debugging is already supported by cloud providers like AWS. The cons are that application itself is still running in simulated environment on local, not on the real target environment. Most of the service applications are triggered asynchronously from the event sources like SQS, SNS, Kinesis, and so on. And on local, you need to simulate the events to trigger the function. And in the real environment, service applications are expected to run with the given permissions of associated roles. But on local, it might not be very straightforward to use the same role and might require extra development effort or complex configuration setups. And the another disadvantage is that consumer services and resources might be reside in VPC, and by default these services and resources are not accessible from the local. So you may need to have a VPN connection from local to access those services and resources, and this requires extra effort to set up and security of this private connection infrastructure. And after discussing pros and cons of the previous approach, so it is seen that either application or external services are simulated and run on local. So in fact, requiring simulated and local environments are the key problem behind the reason why these classical debugging approaches don't fit for serverless world. So it is obvious that debugging should be handled differently in serverless world rather than traditional ways. So in here, I will introduce new ways of debugging service applications: offline debugging and online debugging. These approaches target different stages from development to production, as they are solving different problems. During development phase, developers tend to use their IDs to debug local or remote applications in a traditional way by putting breakpoints. However, on production, they are looking for other ways to debug their applications, as pausing application on production is not acceptable. And at this point, there are some approaches which allow recording code execution by collecting detailed tracing or debugging data and replay it later, which is the reason why we call it offline debugging. Debuggers have always been one of the de facto tools of developers because Whatever we code, there are always bugs, and most of the time you find the bugs during development and testing by debugging. Although debuggers are mostly used for debugging applications on local, they are also used to debug remote applications because you may not reproduce the issue on your local, so you may want to debug it on the target environment, as it may not be easy to have the same setup, same environment on your local. The remote debugging requirement is also valid for AWS Lambda platform and even more important than VM-based environments. But classical remote debugging approach don't work on AWS Lambda environment. The reason is that debuggers work by attaching to remote application process, which is not allowed on AWS Lambda platform as incoming connections are blocked, and also even incoming connections are allowed. Since there might be multiple Lambda containers running, it is not feasible to put the breakpoint to the process exactly, which will handle the request to debug. So because of the limitations of serverless environments mentioned before, the possible solution is having a broker between local and serverless environment. We call this intermediate component debug broker. Debug broker is basically a bridge between your IDE and function and orchestrates network communication between them. Because of the nature of the debug broker approach, it is stateful and requires one-to-one session between IDE, between your local IDE and the remote service application. So to debug multiple applications at the same time, you need to have multiple sessions for each debugging application. Let me explain how debug broker approach works under the hood. So as shown in the diagram, debug broker sits in the middle of your IDE and Lambda function and bridges between them. Since incoming connections are not allowed on AWS Lambda platform, Lambda function connects to debugger through agent or secure WebSocket connection, and also local IDE connects to debugger in the same way via IDE plugin. And as communication protocol is WebSocket, it is bidirectional, so the broker server can push the data from one to another, from your IDE to Lambda function, from Lambda function to your IDE on local. Let's continue with the offline debugging. And classical debugging approach during development, is based on putting breakpoints in the code. But then, when the code execution is reached one of those places, the execution is paused. So you can check the application state, by looking at the values of local variables, argument properties, and trace back in the call stack, and so on. And although this approach is very useful during development to find the bugs, unfortunately, it is not feasible on production because of some reasons. The first and obvious reason is that it pauses the execution, and pausing the application is one of the things that you definitely don't want to see on production. The other reason is that there can be multiple running instances of the same application, and since debug sessions are stateful and one-to-one, it is hard to put the breakpoint to the correct instance as requests may be handled by one of the other instances rather than the instance you put breakpoint. So because of such challenges of classical debugging approach, it is obvious that the production debugging should be handled in another way. Here, the best fit approach is offline debugging, which is a kind of tracing at the deepest level, because it allows you to trace the code execution on line-by-line basis and capture the snapshot of the application during execution. In offline debugging mode, agent records the code execution at each line of the specified code blocks, where the code blocks can be methods, classes, or modules, and then you can replay the recorded code execution later. And while the approach doesn't stop or pause the code execution and has only a few milliseconds negligible overhead, it also provides detailed information about the code execution in case of error to pinpoint the issue. And in this screenshot, you can see an example of offline debugging provided by Tundra. For AWS Lambda function running on Node.js runtime in this particular example. On the collected execution data, you can play forward and back, and then even step into other traced methods. While doing that, you can also see the values of arguments, local variables, and properties at each step by tracking changes. Okay, it is bug story time. We will see some action. But before continue with the examples, at first I want to introduce our sample application. Okay, we have a sample block side application where user can send, review, edit, publish, and search the blog post. the flow starts with a request from client to the API gateway endpoint, and then this API gateway endpoint triggers post blog post lambda function, which gets the blog post request and sends to SQSQ to be processed asynchronously later, and then the lambda function gets the message and checks whether the blog post is valid or not, and then if it is valid, it writes the blog post to DynamoDB table, and streams of DynamoDB table triggers another lambda function, and which is blog post replicator in this flow, and replicates it to the Elasticsearch to make it available for searching later. I mean, free text searching over the blog post content. So this is the basic architecture of our example application where we are using to produce the bugs on our example. Let me back to examples. And in the first example, we are debugging an issue which is caused by non-sync clocks between clients and application. Here, post timestamp is provided by client, which makes the post request to the backend API through API gateway. And after the blog post is accepted, it is sent to SQS to be checked and processed asynchronously. And while processing delay is also logged to be analyzed as a performance metric later. Let me show the example and debug the application on Tundra platform. Here, as you can see that we are extracting the blog post time from the blog post message itself, and then get the current time while processing the message. And you can see that current processing time and the blog post time has the same value. So normally we are expecting that current processing time will be ahead of post time, but because of the clock synchronization problems between the client and the AWS Lambda platform, it is likely to have delay with positive, negative, or zero values. Let's play forward. As expected, we calculated delay as 0, but then somehow it branches to the else statements. So how it can happen that no delay is able to be calculated here? So the tricky part here is that when the calculated delay variable is 0, as a behavior of JavaScript runtime, its evaluation returns false inside if check. So that is the reason that the code runs through else branch where normally we didn't expect to reach there. Here we used offline debugging approach to debug the issue, as it is not easy to reproduce the issue on local. Offline debugging helped us to record the code execution during problematic requests and let us to replay it step by step later, as we did like this. Let me back to the presentation and continue with the second example. And for the second example, we are debugging an issue which happens intermittently based on the value of the input. The problematic code block checks the blog post content whether there is any banned word in the blog post content, and then if there is any, it fails the validation with an informative error message saying that the words in which it is banned for including. Here, it iterates over the detected banned words but gets undefined value during iteration unexpectedly. The problem is that if the same banned word exists in the blog post multiple times, it is stored only once in the banned word set, because each value in this set has to be unique. But even though the same banned word is stored only once, the code increases the banned word counter each time, so the size of the banned word set and the counter is not in sync. Therefore, it is tried to iterate more than number of elements and fails with undefined items on subsequent iteration. Let me show the most exciting part of our demo. I am switching to my IDE. Here I'm using Tundra Debugger VS Code plugin to debug the application on real AWS Lambda environment. I have started the debugger. Okay, I submitted the request, so I'm expected the plugin connect to the real AWS Lambda function and will hit the breakpoint. Okay, connected the function, so it was about to hit the breakpoint. Okay, so here you can see the actual content of the blog post message, and then let's step over and debug step by step on each line. Okay, we are splitting the actual blog post content and checking each word in the blog post, whether there's any banned word or not. It continue. Okay, we found a banned word, which is server, because in our simple application, server is one of the banned words. So it adds the banned word to the banned word set and increase the counter. Continue over the remaining words. And we find another one, and we edit it into the banned words and increase the counter. Okay, so we have two banned word count, so we are going to reject the blog post, and let's branch to the else statement. So in here we are going to build rejection message, but as we mentioned before, the problem is that, as you can see, that banned words has only single item. Because of the nature of the set data structure, same item can only be occurred once in the set, because every item in the set has to be unique. So we have only a single item. But since we increase the counter multiple times, we are trying to iterate over the banned word set more than the actual number of items in the set. So that is the reason that why we are getting undefined items while iterating over the banned word set. So in this example, we got the benefit of offline debugging to debug in debug in the real AWS Lambda environment. So in fact, the original version of this bug only occurred for specific users at certain inputs. So it was not easy to reproduce and debug on local. But for the sake of simplicity of this demo, we just adapted the original issue to our sample application. Thank you all for listening to me. So I hope you liked the demo and I was able to give some more useful insights on debugging service application. Stay safe and healthy.